Hi everyone, welcome back to CHE 101. This is Clarice Halago, and today we'll be focusing on portrait or particle transfer with a specific focus on size reduction. Here's what we'll be covering in this session. First, an overview of size reduction, followed by the energy required for size reduction and as well as some relevant relationships, and finally, some sample problems to test our understanding of the topic. Let us start with the basics. Size reduction, also known as comminution, is the process of breaking down solid materials into smaller pieces. And this isn't just for convenience. It actually increases the surface area of the material, which can really boost processes like dissolution, catalysis, or extraction. Basically, anywhere contact between solid particles and other phases matters, size reduction plays a huge role. Some of the common equipment used for these are crushers and grinders. Now, an efficient size reduction equipment should ideally do three things. First is to handle large volumes of material. Second is to use little power as possible for each unit of output. And lastly, to produce consistent product with a specific size or size distribution. There are four main ways size reduction can happen, and each has its own strengths. The first one is compression, wherein the material is crushed between two rigid surfaces. It is best for coarse reduction of hard materials and doesn't produce many fines. The second is impact. Here, particles are struck with force, causing them to shatter. It's versatile, good for producing a wide range of sizes from coarse to fine. The third is attrition. This involves friction. Particles rubbing against each other or a surface. It is ideal for soft, non abrasive materials and gives you very fine powders. The fourth is shear or cutting. This is slicing. Think of scissors in action. It gives uniform particle sizes and sometimes specific shapes with minimal fines as well. Now, like any industrial process, energy matters. In fact, energy consumption is often one of the biggest costs in size reduction. That's why being able to estimate energy requirements is so important. We usually do this through empirical laws, formulas derived through observation and experimentation. The three most well known are Rittinger's law, Keck's law, and Bond's law. Let's walk through each of them. Rittinger's law tells us that the energy required for size reduction is directly proportional to the new surface area that's created. The assumption here is that the crushing efficiency stays constant and doesn't depend on particle size. If we assume particle sphericity stays the same, then surface area is essentially inversely related to particle diameter. It is given by this equation where E is the energy, P is power, M is mass flow rate, Kp is Rittinger's constant, and dP1 and dP2 are the initial and final particle diameters respectively. This is often used for fine grinding, where surface area creation is significant. Keck's law, on the other hand, takes a different approach. It's based on stress analysis within the elastic limit and says that energy required is proportional to the reduction ratio, such as a logarithm of the feed size over the product size. So instead of surface area, Keck focused on percentage reduction. That means that the same energy is needed to reduce the size by 50%, no matter whether you're going from 100 millimeters to 50 millimeters or 10 millimeters to 5 millimeters. It is given by this equation where k sub k is the Keck's constant and the logarithmic term is the mentioned reduction ratio. This law works well for coarse crushing where changes in surface area aren't as important. Finally, we have Bond's law, which sits between the two. Bond proposed that the energy required is proportional to the square root of the surface to volume ratio of the product particles. This gives a more balanced estimate for many practical cases and bridges the gap between Rittinger's and Keck's laws. The surface to volume ratio is given by this equation where the sphericity and particle diameter are considered. Bond also introduced a really useful concept, the work index. This tells us how many energy in kilowatt hours per ton is needed to reduce the material so that 80% of it passes through a 100 micron screen. Here's a table from the Perry's handbook showing the work index values for different materials, useful when you're doing actual calculations. And finally, here's a general formula for Bond's law, and considering the work index, we arrived at this equation. Compared to earlier wherein the dP2 is the final particle size, here dP2 is the size at which 80% of the feed or product passes through. Now that we've gone through all these three laws and their assumptions, it's time to apply them. Let's work through a few sample problems together to see how these equations work in practice. For the first problem, it is found that the energy required to reduce particles from a mean diameter of 50 millimeters to 7 millimeters is 35 kilojoules per kilogram. Estimate the energy requirement to reduce the same particles from a diameter of 30 millimeters to 40 millimeters, assuming A. Kick's law, B. Rittinger's law, and C. Bond's equation. We list the given values. In the first case, dp1 is 50 millimeters, dp2 is 7 millimeters, and the energy for case 1 is 35 kilojoules per kilogram. For the second case, dp1 is 30 millimeters, while dp2 is 4 millimeters. So our goal here is to solve for E2, the energy needed for the second size reduction under each of the three laws. Listing all the equations we have, we can now solve the problem. Now there's two ways we can go about in solving this. We can either consider case 1 first, then solve for the constant, then plug it into case 2 to solve for the energy. But that's a couple of steps, right? So what we can do to limit the calculation is to use the ratio of the two energy equations to cancel out the constant. This simplifies the math and saves time, so we'll go with this approach. Take Keck's law, for example. It is given by this formula. Taking the ratio of energies from case 2 and case 1, the constants cancel out to obtain this equation shown on the slide. We then substitute the values and solve. We arrive at an energy value of 35.87 kilojoules per kilogram. Now, applying the same principle to the succeeding laws, we get this equation for the Rittingers. Substituting values, we get 61.72 kilojoules per kilogram. As you can see, this energy requirement is significantly higher than that from Gick's law. That makes sense. Rittinger's law focuses on surface area, which increases rapidly with finer grinding. Let's now consider a third method, which is Bond's law. Applying the same principle, we get 46.97 kilojoules per kilogram. This value, as we can observe, lands between those from Gick's law and Rittinger's law, which is exactly why Bond's law is often called the intermediate law. So to summarize, here's the calculated energy values for the three laws. Each method gives us a different result based on its assumptions. The choice of law depends on the nature of the material and the scale of size reduction. In real applications, Bond's law is often the go-to method because it balances the assumptions of the other two. And with that, we've solved our first size reduction problem. Let's move on to the next one. A gyratory crusher is used to crush limestone, with the feed consisting of nearly uniform 40 millimeter spherical particles. Given the screen analysis of the resulting product shown on the side, the screen analysis shows that 3.3% of the crushed product passes through the mesh size 4 but is retained on mesh 6, while 10% passes through mesh 6 but is retained on mesh 8, and so on. We are then asked to estimate the power required using Bond's method, assuming the crusher processes 30 tons per hour. Again, we list the given values and determine the required value. Next, we process the given product specifications because to apply Bond's law, we need the product size at which 80% of the product passes. So we'll process the screen analysis like this. We first list the mesh screen sizes and their respective diameters in millimeters. These values may be obtained from standard tables such as the appendix section of the Giant-Coplis textbook. Then let us convert the cumulative weight percent passing through each mesh. We start from 100% as all particles pass through mesh 4 and subtract the weight retained in each screen. For example, we start with 100. Then through mesh 6, 3.3% was screened, so we subtract that from 100, obtaining 96.7. Doing the same with the next rows until we reach the final value of 0. Now that we have the cumulative percentage passing, we locate the mesh range where 80% passing occurs. From this table, this falls between two mesh sizes, between 85.9% and 67.9%. We then interpolate between the corresponding diameters to estimate the particle diameter at 80% passing. For this example, we calculate a dp2 value of 2.1290 millimeters. You may also determine the polynomial equation for these data for a more precise answer, but for this example, we'll only interpolate for a simplification of the process. Now that we have that, we need one more value, which is the work index. So again, referencing the table, we see that the work index of limestone is 11.61. Substituting all the values, we calculate a power requirement of 50.90 kilowatts. So the power required to crush the limestone using a gyratory crusher as per Bond's method is approximately 50.90 kilowatts. That's all for the sample problems. Let's wrap up with a quick recap of what we've covered in this video. First, size reduction improves surface area, making it vital in chemical processes like extraction, dissolution, and catalysis. We've also looked at four key mechanisms: compression, impact, attrition, and shear. Then we focused on energy consumption and introduced three empirical energy relationships. First is Schrodinger's law, which is based on surface area. Second is Kick's law, which is based on reduction ratio. And lastly, Bond's law, which is based on the surface to volume ratio and is an intermediate case between the other two laws. If you have any questions, you may reach us through any of the following channels. Again, this has been Clarice Hilaga, and thank you for listening.